Before I get started, I would like to say thanks to Chemical and Engineering News for this wonderful opportunity, and of course extend a warm congratulations to all of the other awardees. So before I get started, I'd like to tell you a bit about myself. I grew up in the foothills of the Blue Ridge Mountains in South Carolina, and I grew up playing a lot of outdoor sports. And so actually, this is how I paid for college. I went to Lander University, a small liberal arts college, on a softball scholarship. And you can see here this picture of the lovely team that I had the opportunity to play with. Lander, like I said, was quite small. I didn't have the opportunity to do a lot of research, but I had one small research project during my studies. I was studying chemistry and mathematics. And this research project was with an organic chemistry professor, Dr. Pete Vajan, and he is actually the person who inspired me to go to graduate school. So one day I was in the lab working, and he came in and he sat down and he said, "Wendy, where are you going to school? Where are you going to graduate school?" And I said, "I think I'm not cut out for graduate school." He jumps up and he says, "If I made it through graduate school, you're going to be amazing." So he ran into his office and he came back and he held a document and he said, "By next week, you should have filled this out." And actually, that was my first graduate school application. And so I ended up studying for my PhD under the guidance of Professor Shoji, who was working on low-dimensional magnetism and learning to characterize basically inorganic materials. Wonderful time at Clemson. Dr. Who taught me basically how to do science and write papers and proposals, which you can imagine is really important at this stage in my career. After Clemson, I decided that I wanted to get a bit more well-rounded and do some advanced characterization. And I applied for a position with Dr. Craig Brown at the NIST Center for Neutron Research, and he really gave me an opportunity to do neutron scattering despite the fact that I had no previous experience. During this time, I also wrote a proposal, and it ended up that I received a fellowship that paid for my studies during the time with Craig. One day during my second year of my postdoc, Craig came in and he said, "The NIST Center for Neutron Research is going to be shutting down due to an expansion project. And basically, what would you like to do?" And of course, without thinking, I said I'd like to go to Berkeley and study under the guidance of Jeff Long. So during my studies at NIST, I was looking at small molecule interactions in porous media. Jeff is an expert in metal organic frameworks, so this seemed like a good next step. Craig phoned up Jeff. They talked. They set up a way for me to basically go and live in Berkeley and study. After that, I returned back to NIST to finish my postdoc. Jeff phoned me one day and said, "Wendy, I know you fell in love with California and you really want to come back. There's a job at Lawrence Berkeley National Lab that you should consider applying for." So I looked into it. I ended up applying for this position, and 3 months later, I was lucky enough to be moving back to California. I was working at the Molecular Foundry, basically starting a new user program focused on the synthesis and characterization of porous materials under the guidance of Amar Yagi, who is one of the individuals credited with actually founding the MOF field. During this time, I basically had an opportunity to set up my own research program. And so I decided that I would go after faculty positions. And after looking around a bit, I applied for a position at EPFL in Switzerland. And of course, since I've been here, I've stuck with my American roots. I'm still playing baseball, you can see. But I'm also learning French and learning to ski. And if you can see the hole in my pants, you'll note that I'm not staying on my feet very much. So more importantly, I'm surrounded by this beautiful country that inspires the chemistry that we're doing every day. So we're working on environmental based work in our lab. And this is part of our team. So wonderful group of people. I have the opportunity now to give back what these individuals you see before you have so graciously given to me. So I have the opportunity to mentor a group of scientists now at EPFL. And so with that, what we're doing, we're basically working on constructing porous materials known as metal organic frameworks. These are the most porous materials in the world, and they have a lot of benefits that they can positively impact our planet. Throughout my talk, you'll see that I have these sustainable development goals, so symbols, and you can look for those. MOFs can make a really strong impact in achieving these 2030 goals. So what is a metal organic framework? It's classically defined as a material that's constructed by metal ions or metal ion clusters, shown here in blue. And these are interlinked by organic-based ligands. And these predefined organic ligands are fantastic, right? They give us a lot of chemical tunability. So you can imagine that we can tune their shape and their size to tune the pore shape and the pore size of the material. Furthermore, we can functionalize the surface of those materials and kind of control how these materials interact with their surrounding environments and, of course, guest species that are going to go inside. So if you take a closer look at this material, you'll note that it has very high densities of very small pores, so it's mostly open space. And as a result of this high density of nano-sized channels, they actually have record-breaking surface areas. So the record at the moment is about 7,800 meters squared in a single gram. And just to give you an idea of how much surface area this is, it's equivalent to that of a European football field. So not only can we chemically tune them to selectively grab certain guests, we also have very large surface areas, and this means that we can put a lot of things inside. As a result, my group is working on separations. The reason that this is so important is because currently about 15% of global energy is expended industrially on gas and liquid-based separations. And I should tell you, this number is already huge without the implementation of large-scale carbon capture. We would expect that that number would go up significantly should we implement this on large scales. So really, our group goals, I would tell you, are twofold. It is to reduce the energy input into existing gas and liquid-based separations. And the second is to basically try to make separations that are deemed impossible now possible through the design of new porous materials. So for me, I believe the most important separation of our time is, of course, related to the capture of greenhouse gases like carbon dioxide. As you probably all know, this is implicated, of course, in global warming. The key is that if we want to capture CO2, we have to know where it comes from. And the two largest point sources are going to be automobile exhaust, as well as large-scale power plants used to produce electricity. So here you can see one of those flues coming out of a power plant, and basically carbon dioxide coming out of the flue is mixed with lots of different small molecules like nitrogen, water, and oxygen. And the key is that these small molecules have very similar sizes and shapes. And so if we want to capture CO2, we really have to design a material that has molecule-specific interactions on its internal surface. So then what we can do is simply stream these materials through, or stream the gases through our materials. We can capture that CO2, as you can see here, and then we can emit the less harmful gases, for instance, into the atmosphere. Once our materials are saturated, you can, for instance, heat those up and release that CO2 if you wanted to store it, for instance, long-term underground. Or if we've been super clever, we've maybe engineered reactive sites on the inside of that material so that we can then activate that CO2 and potentially convert it back into value-added chemicals and fuels. In addition to CO2 capture, another extremely important separation, of course, is water purification. As humans, it's required, of course, to sustain life. Unfortunately, about 11% of our population has no access to clean water. We expect with continued climate change, this number is going to rise dramatically. So what we're doing is basically trying to design porous materials so that we can extract some of the most harmful contaminants in water. And so here I'm showing you a MOF. We've done something a little bit unique. We've learned how to append short-chain polymers inside our MOFs, and what you'll note is on this polymer backbone, it's really got some nice functionality that can complex, for instance, heavy metals in water. The key is that these short-chain polymers basically enhance the MOF performance quite significantly. And so that's what I'm showing you here. You'll see lead on the left and mercury on the right. So in the gray, you'll see the initial concentration of lead and mercury. We've treated it with our metal organic framework. In red, you'll see the concentrations decrease a little. However, when we treat it with our composite, our MOF polymer composite, we see that the extraction efficiency is improved by factors of 60 and 90 times. So we get below drinkable levels and within a matter of seconds, and we can take up large quantities of these metals. Interestingly enough, the materials are also extremely selective. So what this means is that if we put our materials in a very complex matrix, it doesn't decrease its efficiency. So here I'm showing you an extremely complex matrix, that's seawater. What you'll note is that the concentration of sodium is 14,000 times that of the lead that we've spiked in. What we find is that the material will selectively remove the lead and leave behind these other metals in the solution, which is great. Because of the material's performance, we've begun incorporating them into filter devices. So we form these little MOF beads We flow contaminated water through those. So here you can see the starting concentration of lead, 600 parts per billion. We note that when we flow it through, we're well below the EPA limit. It's about 15 ppb, which is what is deemed drinkable by the EPA. And what we find in this flow-through experiment is that we can actually purify with a single gram of material about 10.8 liters of water. And this is great because it's already competitive with commercial adsorbents. Furthermore, we know that we can improve this quite a lot with improved polymerization as well as better structuring processes to form our beads. The selectivity that you saw in the previous slide really excited me quite a lot. So I began to think of other ways that we could apply these materials, and the first thing that came to mind were high-value metals. So high-value commodities, and the reason is because the mining industry consumes loads of energy. And so the key is that we then incorporate these metals into a variety of products, like everybody uses cell phones. But the problem is that at the end of their life, we're basically throwing these cell phones into landfills. And so because we would like to make this process circular rather than linear, like it is at the moment, we're basically trying to design porous materials so that we can now extract those precious metals from a variety of different types of waste streams. So here I'm showing you the same exact MOF, but we've basically changed our polymer inside. Now we're able to selectively extract gold from a variety of different waste streams that includes industrial wastewater, sewage sludge, electronic waste, river water, and we've already also begun to see some gold concentration from the sea, which is very exciting. So I can't show you all of these different matrices, but I'd like to show you at least one. We're all familiar with what this is. This is a CPU that we've taken from an old computer. If you look, you'll see that it mostly consists of copper, nickel, and gold. We've basically just grinded these metals off, then we dissolve them in a solution. We throw our sponge inside. Okay, so what I'm showing you here is that we can selectively extract the gold and leave behind the copper and nickel. And I note that the copper has a concentration that's 200 times that of the gold. And despite this, our material still selectively extracts the gold. We can basically then concentrate that gold inside. And what we essentially do once it's full, it's reached its capacity, which is about 1 gram of gold per gram of composite. We then destroy that sponge, and what we're left with is 23.9 karat gold on the back end. This is the highest purity reported to date for such an extraction process, and this is directly related to the material's high selectivity, as I mentioned before. So if you look at the extraction, it's about a little over 600 times more selective, for instance, for copper than it is, or for gold than it is for copper. So with that, we are continuing to design materials, hopefully highly selective materials for a lot of different types of separations. We would essentially like to be able to get the holy grail, and that is begin to mine things, for instance, from the ocean. For the materials that we have that are performing well, we're starting to scale those materials up. We're doing so using green chemistry, so this synthesis, for instance, is done in water. Furthermore, we're learning how to structure our fine powders. In order to incorporate these into large-scale filter devices, we have to form these bead-type structures. And so we're learning how to do this structuring process for essentially an ultimate demonstration where we can show that these materials perform in a lot of different waste streams. So with that, I have to thank this wonderful research team that I've had the opportunity to work with over the last 5 years. Without them, of course, I would have nothing to show you. They're just wonderful people. Furthermore, I have to thank the funding, which makes our chemistry possible. I'd like to thank you all for your attention, and I'm happy to take any questions.
Thank you so much, Wendy. I have a question from the chat where someone asks, how much do the MOF composites cost?
So it depends on the scale. We estimate that if you were to produce these on the ton scale, that you're well below $20 per kilo. So if you consider the cost of gold, this is actually quite exciting because 1 kilo of gold is like 55,000 USD, I think. So it's quite a large markup. Of course, at the moment we're working on gram scales, and the synthesis that you saw is a 400 gram scale. So we're going to have to work on bringing that cost down with scaling. So.
And that was another question someone asked, how scalable are these materials?
I mean, this material is super scalable. You can even make it at room temperature. So, and we're doing it in water. which is really nice. So I don't expect to have any problems with getting up to large scales. And there are even companies that have been producing these materials now on the ton scale for quite a while.
Are there any plans for you to start a company around these materials?
Yeah, we're in the process of doing that at the moment. So it's really exciting.
Sorry, there are so many questions here. How sustainable are the precursors?
Well, we're using iron, which is, everybody's been talking about cheap, and of course it's sustainable. The ligands are relatively cheap as well. Of course, if you can produce the ligands in a sustainable way, I have to assume that they come from, like most carbon-based precursors are coming from oil and things like that. So yeah, I think overall these materials, because of the building blocks that we're using, they're easily made.
All right, I think we'll move on to our next speaker. Thank you so much, Wendy.
Sure.